Welcome to Unit 10, Lesson 3, Proving Identities. So up until this point, we've learned about what the identities are, and I won't lie to you, this section of the unit and of the course is going to take a little bit of grit on your part. You're going to have to really focus and get creative and work really hard to do well in this area because it can be quite challenging. Even I struggle with it sometimes, seeing the answer clearly. So just try to be confident. And then the other thing that you want to consider is to just break the left and right hand side down into the simplest terms possible. That's really the goal here, and you'll see it as we go through the lesson. In part A, verify versus prove that an equation is an identity. So in part A, verify that 1 minus sine squared x equals sine x cotan x for some values of x. Determine the non-permissible values, work in degrees. We're using 30 degrees. You probably wouldn't want to use any intervals of pi here or any intervals of 90 degrees because cotan x will have that undefined value in the denominator. So 30 degrees is a pretty safe standard angle that you can kind of just plug in and see if they're equal. So notice in this question, the wording is very important. They say verify. So here you're going to plug the value in. Now, wherever there's an x, we're just going to put a 30 degrees, and then you just sort it out and find the value. Now, when we use 30 degrees for this question, at the end we come out to an answer 3/4 equals 3/4 on the left hand and right hand side. This should work for all permissible values. So as long as the value that you're plugging in there is defined in all terms of the equation, then you should always get a solution. If you pick something that's undefined, you might end up with something that is not working out to equal. So we can verify that this equation is true for 30 degrees. In part B, prove that 1 minus sine squared is equal to sine x, cos x, cotan x for all permissible values of x. So what we want to do here, instead of using a value, because we're not given any value in the question, what we want to do is simplify the left and the right hand side down until we have a common term on both sides. So you really need to know your component parts of each of the trig identities and know what they equal to. I'll just remind you again that you have them all here, specifically the double angle identities at the bottom on your formula sheet. And then you also have the Pythagorean identities up here. So if you're lost going, what the heck, where did those numbers come from or those values come from? Look to your formula sheet first in those two sections, and it may help you to isolate your variables. Now, when we reduce down the left and right hand side, we end up with cos squared x equals cos squared x. And therefore, the left side equals the right side. And we know that this is true. However, we do have a non-permissible value at 180 degrees n, where n is any integer. So just be conscious of these terms that you're dealing with that will give you an undefined value. Of course, that is what creates that 180 degrees n there. In part B, prove an identity using double angle identities. Prove that tan x equals 1 minus cos 2x divided by sine 2x. So on your formula sheet, you're going to be looking in this section specifically to help you solve this problem. Now again, we are going to simplify left-hand side and right-hand side. Now left side is already just tan x. If you needed to, if you couldn't see into the future or remember what it equals, you could also simplify it to sine x over cos x. But you would want to change it back to tan x at the end to get that equivalency statement. Now, 1 minus cos 2x. That term cos 2x, it can also be equal to 1 minus sine squared x. So that's this one right here. And then on the bottom, the only one that you're really going to run into making a decision with is cos 2x. Sine 2x and tan 2x just have one formula for them. So sine 2x is equal to 2 sine x cos x. Now, on the top, you can simplify away. 1 minus 1 will give you 0. And then this will leave you with 2 sine squared x on the top. Now, 2 sine squared x divided by 2 sine x, that just leaves us with 1 sine x available, divided by cos x, which is, of course, tan. So fill in with your double angle identities and then cancel out common factors. And therefore, we can say that the left side equals the right side, or tan x equals tan x. And because of that, this equation is true for all permissible values of x. In part C, prove more complicated identities. So the first question is, prove that 1 over cos x divided by sine x is equal to sine x over 1 plus cos x for all permissible values of x. You want to pick one side and leave it alone, specifically in this question because the cos and the sine are already kind of the simplest terms that we can use in terms of trig identities. So the left-hand side, we're going to leave that alone and we're going to make the right-hand side equal to that. So we start with sine over 1 plus cos x. Now, we need to create sine x on the bottom. So what you're going to do is multiply both top and bottom by the conjugate of 1 plus cos x, which is 1 minus cos x. Now this does a really nice thing in the bottom for you. We are trying to create a situation where we have a sine x on the bottom, and you end up with this statement, 1 minus cos squared x. And if you look to your formula sheet, we have this statement here. It's one of our Pythagorean statements. Sine squared theta plus cos squared theta equals 1. Or 1 minus cos squared x equals sine squared theta. Okay, so that's where that value is coming from. So now that we have this 1 minus cos squared theta, or cos squared x, we can say that that is equivalent to sine squared x. And then we will just keep it simple. So we'll cancel out the sine here. Sine divided by sine, we're just left with 1 sine x. And then on the top, 1 minus cos x. And therefore, we have proved this formula. So you do have to get a little bit creative and try and find, where can I manipulate this formula to create the situation that I'm trying to solve? And that can be a little bit daunting at times, but just use your formula sheet and see what you have. Many times there will only be one choice when you actually consult your formula sheet. So just be confident and use that tool with you. Our last example, D, prove an identity that requires factoring. Prove the identity cotan x minus cosecant x is equal to cos 2x, double angle identity, minus cos x, divided by sine 2x, double angle identity, plus sine x for all values of x. So our left-hand side, we just want to change that into some simpler terms. So we know that cotan x is equal to cos over sine, and cosecant x is 1 over sine. And we can combine these because they have a common denominator. So just think of it in terms of fractions. If you're dealing with a fraction, they need to have a common denominator to add or subtract them together. So that's what we're doing here. Sine x, same thing. So we can just combine that top term and have one common bottom term. Now, on the right-hand side is where it gets a little crazier, and you just need to break it down into kind of its component parts to see where your answer comes from. So we have cos 2x. If you look on your formula sheet in your double angle solutions, we can replace this value with 2 cos squared x minus 1 and minus cos x. That stays the same. On the bottom here, we have 2 sine x cos x, which replaces sine 2x, plus sine x. in the top, in the next step, what we're going to do is just reorder our polynomial. So we'll have it in descending exponential order. In descending exponential order. So you'll have 2 cos squared x minus cos x minus 1, or a squared plus bx plus c, right? And in the bottom, you can factor out the sine x. So you'll divide both terms by sine x, and you'll be left with 2 cos x plus 1. The next step here is to factor out that top polynomial, 2 cos x plus 1 times cos x minus 1. And then you can just cancel these common terms, and you're left with cos x minus 1 divided by sine x. So notice how in the bottom here we kind of manipulated out that sine x to create the same situation as the left-hand side. That's kind of what you want to be looking for when you're doing these problems. Unfortunately, there's no real trick of the trade to solve these problems. It's all practice and consistency. So as you do more and more of them, you'll start to see the patterns and it will become very familiar. And in light of that, you have practice questions beyond this, and you can do them to prepare for class tomorrow.